So the beautiful thing is, now that our data has no missing values and is turned all into numeric values, we should be able to build a machine learning model. So let's do that. We've instantiated one way back up here as model, way back when we started the modeling section. Far out. We've covered a fair bit of ground here. You should be proud. Modeling, wonderful. We're going to do basically the exact same thing. So let's build a machine learning model. We could copy this, but we're just going to write it out again. We'll leave a bit of communication to ourselves. So now that all of our data is numeric, as well as our data frame has no missing values, we should be able to build a machine learning model. Wonderful. So remember what our goal is? It's to find patterns in the data to predict the sale price. So that's what we'll have to do. Let's have a look, dftemp.head, one last look at our data before we model it. So we need to drop the sale price column so that we can build a machine learning model that takes in all of the other columns except for sale price, finds the patterns, and then tries to predict sale price. So what I'm going to do, I'm going to set up a little timer magic. And if you haven't seen this before, the percentage sign, that's a Jupyter Notebook magic function. You can search up for a whole bunch of these, but what this is going to do is basically just calculate how much time this particular cell takes to run. And I'm going to do it on my computer, which is a MacBook Pro. How many rows do we have? We have 400,000 or something rows. This may take a little while. In previous examples, when we've worked with less data, our machine learning models have been pretty quick, right? Because it's only have to sort through a couple of hundred rows, but this is 412,000. I mean, of course, there are much bigger data sets, but we're starting to get up there, right? We're in the hundreds of thousands of samples. Instantiate model. So what this time thing is going to do is, because it's our goal as a data scientist, as a machine learning engineer, is to do as many experiments as fast as possible. If you're training models on all of the data all the time, it's going to take a fairly long time. So I'm just going to demonstrate how long it takes for my personal computer to use a baseline random forest regressor model to find all the patterns in all 412,000 rows. So don't worry, you're not going to have to sit there and watch it run. Once we kick it off, I'll pause the video and then come back and show you how long it took. The ways of thinking I want you to start thinking about is, when you're doing experiments, start to think to yourself, how can I reduce the amount of time it takes between my experiments? The reason being is because you're not always trying to do the right thing. You're trying to figure out what's wrong, what doesn't work. So that's the rationale between trying to speed up your time between experiments. And as I type that, as I talk, what we're doing here is we're just instantiating a random forest model. We're going to put random state equals to 42 there. Random state equals 42. That way our results will be reproducible. So this is all we're doing. We've imported the random forest regressor class because we're working on a regression problem. We're setting n jobs to equal -1 because this is a fairly large data set for what we've been working with for now. So I want to use all of the cores on my computer, and I want random state to equal 42 so our results are reproducible, and I'm going to fit the model to the data. So this is our X and this is our Y. Remember, we're trying to predict sale price based on all the other columns except for sale price. So when I kick this off, this will take a few minutes, but I'm going to pause the video, and because we've got the little magic function time here, we can see how long it takes. So get ready to time travel in 3, 2, 1. All right, we're back. That was pretty quick, hey? So our model is finished, and it says here that the wall time was 6 minutes and 58 seconds. So it took about 7 minutes to go through 412,700 rows, which is actually pretty good, right? Think about how quickly you could look at that. How long would it take you to go through 412,000 different examples? You didn't have to wait for that time because I sped it up, but if you were to run this on your computer, it may take longer, it may take less time, depending on what sort of computer you have. I'm running this on a 13-inch MacBook Pro, I think from about 2016 or something like that. I'm not even exactly sure how much computing power mine has, but it's a laptop, so maybe not as much as a desktop. Anyway, but you can imagine as these numbers of rows started to really get up high, this could start to take a long time. If our goal as machine learning engineers, if our goal as data scientists is to reduce the amount of time between experiments, we're going to have to be pretty nifty when we try out different models, when we work on different data, because waiting 7 minutes every time, even if this number was higher, for a cell to run, that's going to slow us down a fair bit. So we'll see a little trick soon of how we can improve this, but why don't we score the model? So see how our model did. If it's gone over 412,000 rows, surely it's found some patterns in here. So we're going to score it on just the exact same data that it was trained on. So we'll copy this. And now remember, for a regression algorithm, the default score value here is going to be return the coefficient of determination, which is the R squared. Now, if you need a refresher on what R squared is, you can go, what is coefficient of determination? But in other words, it's a score that can go up to 1. It's 0 if all your model does is predict the mean of the sale price column. And it can go to negative infinity if your model is absolute terrible. So we're looking for a value that's close to 1. So again, this might take a little while because the model has to compute the score of how it did across 412,000 rows. Boom! 0.98. Wow! If the maximum is 0.987, so closer to 0.99. So if the maximum is 1.0, does that mean our random forest regressor has almost found a perfect pattern for predicting the sale price based on other columns in the data frame? Not so fast. I want you to think about, before we get into the next video where we're going to cover it, why is this metric not reliable? Right? So if we have a look here, we fitted the model on this data, and then we've evaluated it on the same data. Why doesn't this metric hold much water? Have a think about it. We'll talk about it in the next video.